Hey guys, in this video you're going to learn a whole bunch of optimization techniques to help you keep your game running fast and smooth. Ready? Let's go. So if we hit play and we go to Window, Analysis, Frame Debugger, and we hit Enable, this tool will let you step through all the draw calls to see step by step how Unity is rendering your final image for that frame to your screen. And you'll notice for me that under the Draw All Renderers section, I have 5 draw calls. I've got the background, the floor, the enemies, the player, and the player's weapon. And right now this makes sense because all of these are separate sprites that have been imported into the project. But it would definitely be faster if we could use fewer draw calls to achieve the same result. And we can do that with a sprite atlas. So let's make one. I'm going to right click, create, 2D, sprite atlas. Now we want to add all the different sprites into this objects for packing here. And just note that this has a lot of the same settings as the sprite importer. So if you're using pixel art, for example, you're going to want to change this to point and this to none, for example. And when you're ready, hit pack preview. Now, if we run this and look at the frame debugger, you'll see we only have 3 draw calls. I had expected it to be 1, but you can see it didn't batch the enemies with the player because they have different materials. And if I didn't necessarily need them to have different materials, I could change that. And now they're actually all being drawn with just 1 draw call, which is significantly faster on the GPU side. All right, next I want to move on to scripting and show you one of the most meaningful ways that I've changed performance on the CPU side. So right now on all of these enemies, I have this running in the update function. This here makes them always face the player. And this here is checking for a certain distance threshold, and if it's met, we aggro the enemy to the player. Now, in the grand scheme of things, Unity can run this every frame on many instances of this mono behavior and run just fine. However, this is a complete waste of resources, and there's no need to do it every single frame. While in play mode, if we open up the profiler here, and we just click anywhere on the graph, our game will pause so that we can analyze it. And let's drill down into the enemy behavior update. This is taking up 1.2% of the CPU usage right now. And as we said, that is completely unnecessary. This is every single frame. And so what we're going to do is implement a tick system. This will basically allow us to create our own update function and choose how often we want that to run. So I'm going to create a script called ticker and attach it to my game manager here. Let's set up a float for tick time. And for this, I'm only going to run it every 0.2 seconds. That's still nice and often, so we shouldn't notice a difference in enemy behavior, but we should get a nice performance boost from it. And let's make this static so that we can reference it easily. I'll need a tick timer float. And this is going to be an event, so I'll set up a delegate void tick action and a static event of type tick action called onTickAction. Now in update, we can increment tick timer, and once it's past our tick time, we reset the timer and call our tick event function, which will invoke the event. Now over in our enemy behavior script, I'm going to create a function called tick, and we'll just subscribe to that event in onEnable and unsubscribe in onDisable. And now this tick function will fire every 0.2 seconds. So let's move our logic in there. And there you go, you can see the enemies are still always facing the player, but instead of running that logic every single frame, it's just running way less often, but it's not making a noticeable difference in our enemy's behavior. In my game Samurado, I actually have multiple tick timer events at different time intervals for things I need to happen regularly, but not regularly enough to warrant them being done in update. So you've seen the profiler and you've seen the frame debugger. But when it comes to certain snippets of code, it can be really hard to tell with those tools alone what is actually more performant. And sometimes you just need to test things yourself. So let me show you how to set up a benchmark test to let you run your own tests. And this is actually a lot of fun to do. So I've set up this little benchmarker test script. We can choose between 0 to 1 million iterations to actually get a nice sample size to see how long things take to run. As for getting the button on this script here, that is outside the scope of this video, but if you want to know how to do that really easily, you can check out my video on setting up custom editor scripts right here. But if you don't care about that, then I suppose you could just perform this function in the start method instead, and that would still work just fine. So we need to add the system.diagnostics namespace at the top. We have our iterations float, and I'm actually running whatever function we want to test inside a separate script called benchmark test, just so that we never need to touch this script again. But in order to actually time the number of milliseconds it takes for certain loops to run, We set up a new stopwatch, start it, run our function however many times we set in our iterations, stop the stopwatch, and then print out the elapsed milliseconds. So you saw in our enemy behavior that we were doing a distance check using vector2.distance. And I've actually heard online that this is very slow because internally this uses a square root in the calculations, which is known to be slow. So let's test that for ourselves. In our benchmark test, I'm just going to plug in one of our enemies at random. I really don't care which one. It's just so that I can compare the distance between them and the player. So we'll say, okay, our distance is equal our vector2.distance between the player and the enemy's position. And then we could do something like if the distance is less than the aggro range, then we can do something with this, right? So let's crank this up to 1 million iterations and test it. And it seems to be averaging around 390 milliseconds or so, which, you know, for 1 million iterations is really not so bad. But let's try what I've heard is supposed to be a more performant approach. What we can do is just subtract the enemy from the player and use .square magnitude to return the squared length. Now this returns a less friendly number. We can't just say if the distance is less than the aggro range because this returns a squared result. So what we would do in this case is set up a squared aggro range and raise it to the power of 2. And then we could effectively compare distances that way, which is a bit more of a pain. And if we test this, it's maybe a few milliseconds faster on average, but it's barely enough to even show the difference. So it turns out I will continue to use vector2.distance because I just think it's far more readable and the performance saved using the other methods seems negligible. Let me show you a cool trick and we'll use our benchmark tool to test it. It is extremely common to use strings in our animator just like this. You're going to see that everywhere online. And you'll see it takes a little over 90 milliseconds to complete that 1 million times. But there is a better way because what happens is Unity needs to take this string and hash it behind the scenes afterwards. So we can save time by just doing that ourselves once. So up here, we'll just set up an int called attack trigger and use animator.string to hash and pass in the string there. And we'll pass in that integer instead of a string. And that is saving almost 30 milliseconds. And we want to do the same thing with changing shader properties as well. I've gone ahead and changed the material on my one enemy because I want to change this one color here, which I called tint color. So first we need a reference to the material from the array of sprite renderers. And then we can set the color, again using a string here for the first test. So it's around 615 milliseconds. Now let's try hashing the string ourselves first. You can do that by again setting up an int and say shader.property2id and pass in the int there. This one is a lot faster actually. I'm pretty surprised by this. Okay, next I want to give you just a few more general tips. In your renderer asset, if you know you do not need depth texture or opaque textures, turn them off. Because these ones end up drawing depth or opacity to a texture based on what your camera sees. And that ends up using a lot of unnecessary memory if you don't need them. Okay, next tip, and this is one of the most fundamental ones you will ever hear about. But if you were doing a lot of instantiating and destroying, for example, if you have a game with a lot of bullets, then you will want to implement an object pooling system. There are so many great resources out there online for it, but if you want, I have a video here that shows you how you can set up the same system that I'm using in my game. Another tip, I actually didn't know about this until recently, but if you have empty functions in your script, delete them. Do it to keep your code clean anyways, but apparently there's also a slight overhead cost for each function, even if it's not actually executing anything inside of it. Okay, next, let's talk about import settings. They make a big difference in memory usage. Take a look at my background here. With no compression, it is 6.8 megabytes. With low quality compression, it's 1.1 megabytes. And honestly, I cannot even tell the difference between the two. So this is just an example. This involves a lot of testing, but do it with your textures and your sprites and your audio as well. Just play around with the import compression settings, test everything out and make sure that you're not reducing your quality in a noticeable way, but compression is going to be your friend a lot of the time. And the last tip I will give you is how using scriptable objects can save you memory. You will notice that every single one of my enemies has this enemy behavior script here with some variables on it. Now, I'm just using this as a configuration for this enemy. I have no plans of changing these variables between different enemy instances. Now, when I hit play, every single one of these scripts will have its own instance, and on every single one of those class instances, these variables will have their own copy in memory. And for this scenario, that's completely wasteful. What we could do instead is create a scriptable object and move those variables we don't want to be changing across multiple game objects, and then just plug in that scriptable object. This is also really nice for designers because they just have this nice little asset file to change. And we're not creating dozens of copies of these variables to sit in memory. It's just one, which sits on the scriptable object, and every enemy just points to that scriptable object. And even if you do want different enemy configurations, then you just create another scriptable object asset and plug that in instead. This can also make testing your game a lot easier as well, because you can just plug in different behaviors. I'm going to leave a link for a performance and optimization ebook down below. This can teach you how to do deep profiling, how to avoid garbage collection, and it's filled with lots of general tips to further help you optimize your games. That's all I got, guys. Bye.